Good afternoon, everyone. I think we've heard a lot about the amazing works about concrete related research. So right now I'm gonna just talk a little bit of a different topic. It's about the work that we did at Texas A&M from my colleagues and also my supervisor, Dr. Anand Popala's group. Unfortunately, he cannot make it today, but he did ask me to make sure to thank Jersey and Celeste for the invitation. Without further ado, I'll start my presentation. And so in case you don't know what is the soil stabilization or the subgrade, just to treat it as a polymer concrete, but with a much lower strength. So that's the way to put it. So my presentation today I'll first give a real quick overview about the area, and then I'll use the 3 case studies focused on different aspects of the soil stabilization using polymers, and then followed by that, talk about the opportunities, the challenges, and the potential future work, and then follow with the summaries. So when we talk about the subgrade, it's a part that for people, I imagine most of people are concrete folks here. So in case you don't know, it's just kind of the foundation of a pavement, which is usually the weakest layer. And a lot of times when it comes to pavement design, we focus a lot on the surface layer, let's say concrete or asphalt. However, eventually all those load from the traffic will pass on to the subgrade layer like here. And then eventually the pavement might fail prematurely, and not because of the material on the surface, but because some issue is happening in the subgrade layer, because that's usually not well recognized or well designed for. And let alone there are many other extreme events like flooding. A lot of times it won't affect the surface layer as much, but once the water start to come to the bottom layer, affect the subgrade, it will significantly deteriorate the structure and cause some problems. Here are some of the figures. You see the pavement distresses or damages. A lot of times it's because of the traffic and the surface material, but many other times there are hidden issues down below the pavement from the subgrade. And then from here, normally when we treat such a weak soil profile, we have to stabilize the material. The common ways are, 1, replace those. But usually those are costly, but if you don't mind, go ahead and replace it with the sand. Those are stronger material. And then another purpose is the mechanical stabilization by mixing some aggregates in there without fully replacing the weak soils. And then the third one, which is the one that I'm gonna present about here, is called chemical stabilization. We add some chemicals. Cement is one of them, lime is one of them, and polymers is also one of them. And then when it comes to the design for stabilizer subgrade, we have to consider, just like concrete mix designs, we have to do mixed design as well. We have to consider the stabilizer content, how much polymer we add in there, how much cement we add in there, and then the mixture, how we mix them, how we compact them, eventually the density that we achieved for the structure, and then the curing, of course, and then the mechanical property like strength and stiffness that matters for the pavement. And then lastly, the durability. That's what everybody try to answer, like how durable the material is, and eventually affect our design and the surface life of the pavement. So here a little bit about the background of the first research project. This is sponsored by the Army Corps of Engineers. For this one, we're looking into the resilient modulus, which is a property to measure the stiffness of the pavement or subgrade layers. And for this project, we not only measure that, but also study the other geotechnical property, like the workability of the soil. We call the plasticity index, and some other properties. And here, in this project, we tried 6 different types of soils, from the gravel to sand to sandy clay to lean clay. We even have fat clay, so it was not included here. And the polymer that we used is one of the most popular products that are promoted for soil stabilization. Is the emulsion made of vinyl acetate ethylene copolymer. And for this one, like any other mixed designs, we choose 4, 5, 6% of the product added into the soil. We'll talk a little bit more about this because it depends on the polymer. Sometimes this term itself need a little bit more clarification. We'll come to that later. And then the curing, just a regular standard curing at room temperature. relative humidity. And for comparison purpose, we did compare with the cement and lime to see how this material perform. And from here, these graphs on the on the bottom right corner are the plasticity index. If you, this shows the workability of the material. Usually, we won't have a lot of issue. However, if you have clays, which is a very plastic material, sometimes it's very difficult for mixing it in the field. So that's the parameter we want to see, how adding polymers or other stabilizer will change the plasticity index. From here, these two graphs, you can see that the polymer, when it comes to the sand, it didn't change it that much. Same as for cement, it also just slightly improved, but because it's not relatively a plastic material, so we won't have a major issue there. But when it comes to the clay, this CL soil here, we can see for cement and lime, they can reduce the plasticity, make it much easier to work with. However, for the polymer product we used here, it didn't show much change, which means we could face an issue in the field, depends on how plastic the soil still is after the treatment. And then the second property that we're looking at here are the compaction characteristics. Usually here, the x-axis at the peak value, what is the x-axis? That, let's say 10% here, that's the amount of molding water we need to mix with the material before compaction. It affects the final density as well. And then y-axis is the density that we have to compact the material to that density so that we will reach the best performance of the material. So from here, we can, after we tried multiple soils, we found that in general for sandy soils, the maximum dry unit weight would increase, and the optimum moisture content we add will drop a little bit compared to the untreated soil. However, when it comes to the clay, it becomes slightly different. The density didn't increase that much, and the moisture we needed for compaction actually will increase. And then this is the strength parameter, a quick screening test for analyze how the material would perform. As expected here, if we add more polymers in there, we increase the strength significantly. And also, if we extend the curing time, we can also see an improvement here. And after we tried it in multiple soils, we find out in general, under this curing condition, the sandy soil will give us a much stronger strength improvement compared to the clay soils, which is expected because clay is a much weaker material to start with. And then the parameter for pavement designs, well, some states still haven't used the resilient modulus yet, but there are more and more agencies and the DOTs start to incorporate the pavement ME design into their pavement designs. And here is the interesting results that we found. Even if the strength-wise, we show that there's a significant strength improvement. However, for resilient modulus, if you look at this, technically you can say the numbers are increasing, but from technical perspective, they're basically similar. And of course, we also find that this one is soil dependent. So which means when it comes to the real project, we have to do some screening studies to see what kind of soil we're dealing with. Is this polymer compatible with that soil? What kind of response we're going to get? And then the durability study, one of the issues that a lot of times we face when we use polymer for soil stabilization is the moisture issue. Because we want the material to be durable, we don't want it to get weak when the moisture gets in there. So we also evaluate that in this project. We follow the TechStop procedure to use a tube suction test to measure the dielectric constant values. And from here, you can see after the polymer treatment, the values did drop a little bit. However, if you compare to the table on top here, if the reading is larger than 16, which is, yes, in this case, so that means that the material, after all, even if we have the treatment, is still moisture sensitive. And then the more traditional durability test for any stabilized soils, the wet-dry test, we soak the material after the curing and everything for 5 hours and then dry them and then measure the strength change. You can see there we saw the strength drop immediately after the first cycle. And which shows, well, we really have to re-evaluate this design or maybe look at the product itself to see if it's suitable for this type of soil or not. And also, there's another debate, which is the methodology itself, because it's designed for cement. which likes water and reacts with water. And also we find for many other stabilizers, they actually will fail this criteria. Even if you use all the DOT recommended cement or lime dosages, they'll fail just because the method is such an extreme scenario. You expose the material to 100% moisture, and then right after that, you dry it to really high temperature, and then kind of it's a torture to the specimen. So that's the one part. Now more people realize that about the testing method itself, so we're trying to address those by coming up with a more realistic durability evaluation designs. And then, but we show that the polymer itself give us some durability concerns. So another solution we're trying here is to have a combination of cement, traditional cement, with the polymer itself. What we found out here by mixing with a 3% cement, we found out under the drying conditions, you can see with the polymers, the strength are significantly higher than just using the cement itself, which means the polymer itself also contributes to the strength gain, especially during the drying condition. Which I believe it's because the cement reaction takes time, and for 3 days and 7 days in general is much shorter. However, for polymers, once you dry them, and once you dry them, the polymer will contribute to the strength gain immediately. And we also look at the durability or residual strength or resilient modulus after this. We can see there's still some drop of the resilient modulus. However, it's not like the previous sample that everything collapsed completely. So here are some of basically the types of engineering property we have to evaluate when it comes to polymer treated soils. And then this second project, we look more about the mix design itself. As I mentioned earlier, in one of the slides, we have the polymers. That's just one polymer product. There are probably hundreds of different polymers in there, and they have different properties that are often ignored during the mix design. For example, in this case, the factors that affecting the mix design from the polymer perspective. For this case, we choose the two different polymers. One is negatively charged, one is positively charged, and they have different molecular weight. And you can look on the mix design table here. We use the normal design of the dosages polymer solution by definition of the percent weight of the dry soil. We add 2% up to 8%, and then we change different polymer products. Well, same polymer, but different molecular weights, different concentration of the solution itself, because a lot of times these are ignored in the design because people just buy the polymer product. They don't care what is in there. But a lot of the time those are hidden, which that's why a lot of time if you read the literature, you find like, okay, I used 2% of polymer, it didn't work. That person used 2%, it worked really well. So a lot of times it's because the concentration of the polymer itself is very different. And most likely those information are unknown, either because the manufacturer won't release those information, the people who did the work don't know, or sometimes it's just because some certain polymer cannot have a high concentration while others can have like 50% concentration, while others can only have 10%. So from here, what we did is the effect of the dosages, which is pretty clear by now. The more polymer you add in there, it'll increase the strength. And then on the right-hand side is the effect of the concentration of the solution itself, as well as the molecular weight. So overall, there are some differences here and there, but overall, you can see that if the molecular weight is higher, more or less, it'll contribute better to the strength gain. And of course, the more concentration, it'll be relatively better as well. However, there's a catch. When the polymer molecular weight increases significantly, it'll increase the viscosity as well, which means it'll be very difficult to mix with the soil. So eventually there's always a balance. So you have to consider all those factors. You want it to be as effective as possible, but at the same time, you have to consider the practical application. In soil stabilization cases, the mixing and the compaction is very important. And here is another the positively charged polymers. We can see the same trend when you increase the concentration. The strength increase, we increase the dosages of the solution itself. It also increased the strength. Here you might wonder, well, are you talking about the same thing? You increase the concentration of the polymer, you increase the dosage. Are they literally the same thing? Yes. However, it's very simple. Everybody seems to know that. However, when it comes to mix design, no one really talk about it. So that's caused a lot of confusion for people who designed this. They just added the polymer, treat it as a cement or lime. We add 5% of material in there. Doesn't matter what's in there. That caused a significant disparity in the literature. Like, why some people in the literature say, I only use 0.5% of my polymer in the soil, and it give me a strength like 5 times higher, while another person used 20% of the polymer in there. When other people don't know what's going on, they're like, 20%? No, it must cost too much. I'm not going to use your product. But in reality, it could just because the solution itself has so much water, like 50% is water. So like a lot of times these are, we'll come back to this right after one more slide. We introduced a term to kind of eliminate that confusion to make things easier. But before we talk about that, this is the effect of the curing time for polymer treated soil. And usually like the cement treated soil, we follow whatever we followed for the cement treated soil. We cured it for 7 days, 28 days, sometimes people followed for 1 day. But for people who come from a polymer perspective, they're like, why do you need 28 days? The reaction should be over by then. There's no point to do it 28 days. However, for civil engineering work, a lot of time you have to follow whatever protocol you have to follow. Since there's no protocol out there for polymer treated soil, you say, I want to do this. They're like, oh, you didn't follow the standard or whatever procedure. So sometimes we kind of forced to evaluate those and then show them, hey, there's no difference between 7 days and 28 days. Here's the proof. So that's why, like the third part of the project, we're trying to kind of suggest a protocol that customizes it for the polymers. But in general, yeah, this is the founding that we just found from this research. And here is the concept that I talk about, the polymer, the dosage of the polymer content. There are so many different terms in there, all talk about the same concept, which usually won't exist when you talk about other stabilizers like cement or lime. It's just pretty straightforward. But in this case, we to eliminate that confusion in the literature or between the different researchers or the practitioners, we introduced a new term called effective polymer content, which is not really new. We just want to say, hey, you guys need to kind of like express the polymer content in a better way, more consistent way, so that everybody can understand how much material you put in the mix. So technically, you can just multiply the polymer dosages, if it's a liquid polymer, and then multiply by the actual concentration of the polymer. You get the effective polymer content, which means how much actual polymer you put inside the whole mix. Because most of the liquid polymer, they're water-based, so the water is just there as a media to mix the soil with the polymers, not really for reaction and all those purposes. So eventually, it will dry it out. So effective polymer will highlight the contribution from the polymer itself. And then by doing that, we can have a much direct comparisons between different polymer products, probably different researchers, as long as they report that, or if not, provide both of those information. How much polymer product you put in there, what's the concentration of the polymer product that you're using. But if you look at this, I replot those graphs, just make it much simpler now. So now you look at this, the effective polymer content on both sides now are actually close to 1%. So now if we look at this, it'll be much easier to compare different polymers. I can say, oh, okay, the polymer on the left, which is the PSS, I need 0.2%, seems already give me a 4 megapascal strength compared to the other one, I need a 0.6%, or 1%, I want 8 megapascal. So we kind of know, okay, in this case, I might prefer the PSS over the PTMAC on the right-hand side, just because I can use less material to achieve the same strength. And then here is an example of the, for a clay soil, we can see that for clay, one thing that we notice immediately is that the strength is now lower compared to the sandy soil, which is, again, expected. And then also we need more polymers because clay is a mineral that actually relatively reactive compared to sand. So that means it's more difficult for the polymers to penetrate, to mix well with the soil particles. So eventually that causes a lot of challenges in the mixing, and then it might show in the strength as well. 20 more minutes? Okay, yeah, thank you. So then the third one, based on all this, we did a real quick literature review and a national survey on this topic, and then use those information, plus our own research and other people's research. We tried to propose some guidelines for the synthetic polymer for soil stabilization. And from here, you can see that there are more and more paper, the top one, you can see that there are more and more work started to use the polymers together with other stabilizers to evaluate the synergistic effects. And then other than that, there are tons of polymer here, and each one, believe me, they all give a completely different results a lot of times. And also the methodology that they're using are also very different. However, there's one thing that we find out. Currently, most people just use UCS because it's fast, it's simple. However, depends on the application. Sometimes that may not be applicable, and sometimes it's like not suitable for the project also, or it's just not enough just by the strength. So from here, we asked the same question in the survey: what standard you follow? Most people use whatever is available for cement and lime, and the other people, they come up with their own because they know the existing standards are not designed for this. And then the same thing with the definition of the ratios. Some people use the liquid polymer as is. Some other people do the conversion to expressing the effective polymer content. And other than that, the dosage added, you can see some people less than 1%, some people 5 to 15%. And then curing days from less than 1 day to more than 28 days, and the different drying methods. And also, most of the challenges that they faced are the durability issues. I don't know how to choose the polymer. I don't know how to design the product because there are so many moving factors. And also field application, we need to see more data how this material performs in the field. And other challenges that we identified through this process are like we lack of established consistent standards or protocols to follow, and also very inconsistent results when we're trying to compare different polymers and select them. So from here, we proposed a guideline, which is modified from the traditional soil stabilization because we don't want to change it completely, so that everybody who works in this area can still very familiar with the procedure, but we do highlight something that's very important for the polymer itself. One is to know the material. Know the material means not just what product you're using, what kind of property it has you're expecting, and also what kind of performance you're trying to increase, and is it for a strength improvement or erosion control? And then also, after you identify that, you just design the product to do the preliminary screening test, and at the end to do the field application. So the benefits we can see here is, well, polymer in general, based on our experience, is much easier to applicate, to mix with the soil. It's a really fast, easy mixing, and cure it really fast. And also, it has potential to work with other stabilizers. But the challenges is, right now, we don't have enough data to convince everybody that, oh, if this polymer would work in this scenario, and let alone many other design challenges. However, that also means we have many other opportunities there. It's much needed to design a universal test protocols or standards. And then many other times, it depends on the project purpose. We can have a laboratory study, we can have field applications, or even the synergistic effect of the polymers and other stabilizer like cement. So from here, this is the summary. We can see the polymers have the potential to increase the strength, and however, it does vary a lot. It depends on the soil and the polymer type, which means we have to be carefully select our material, and also the standards are much needed, field application as well. And here are some references, and I would like to acknowledge our sponsors at SANX, and then the Army Corps of Engineers, and the facility and staff at the Texas A&M University. Now I'm open to any questions.